Good day, students. Welcome to Mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 1 to 5 of the June 2019 Geometry Regents exam. Now, this will be a thorough coverage of how to solve the problems on a step-by-step basis. If you would like to have a quicker consideration of the problems, do visit our website at mathgotserved.com under Geometry Regents, where you can gain access to the transcripts of this presentation and go through it at your own pace. Don't forget to subscribe to this video so you can get updates to the remainder of this review series. Alright, let's take a look at question 1. In question 1, we've been assessing how to carry out a sequence of rigid motion transformations, namely translations and reflections. Question 1 reads, on the set of axes below, triangle ABC is graphed. Okay, so we have triangle ABC right here. And then triangles A prime, B prime, C prime right here, and triangle A double prime, B double prime, C double prime. The images of triangle ABC are graphed after a sequence of rigid motions. Okay? Question. Identify which sequence of rigid motions maps triangle ABC onto A prime, B prime, C prime, and then maps A prime, B prime, C prime onto A double prime, B double prime, C double prime. Okay, so what we're going to do is we're going to take a look at each of these rigid motion transformations and see which one will accomplish the transformation of going from this triangle right here, this is the first one, to this triangle, and then from this triangle to this triangle right here. Alright, okay, so now let's take a look at the first statement. In the first statement, we have a rotation followed by another rotation. So a rotation followed by another rotation. So the first rotation basically takes you from triangle ABC to A prime, B prime, C prime. Is it possible to get A prime, B prime, C prime by rotating triangle ABC? The answer is no. Okay, it's not possible because you cannot get from A to A prime by rotating triangle ABC. When you rotate triangle ABC, A prime is going to end up on the other side. Okay, let me show that to you real quick. So we have this configuration right here. So look at this triangle right here. If I rotate this triangle, what's going to happen is that it's going to end up on the other side. Okay, so rotating triangle A prime, rotating triangle ABC will result in A prime being on the other side, and then C prime will be on the left and A prime will be on the right. So that automatically eliminates that first option there. So for option 1 is not the answer. Is not the answer. How do we know? Option 1 is not the answer because A cannot be mapped. A cannot be mapped to A prime on triangle AB, A prime, B prime, C prime by rotation. There's no way that you can do it. Alright, the orientation will shift. Alright, so that means option 1 is not the answer because it fails the first rigid motion transformation. Number 2, a translation followed by a reflection. Okay, so can we get triangle A prime, C prime, B prime by translating triangle ABC? That's the question. The answer is absolutely no. If you translate triangle ABC, B will always remain above segment AC. Okay, so there is no way you can go from B to B prime by translation. It's impossible because B prime is at the bottom and B is at the top, and by translation only it's impossible to get those points to line up. Alright, so option 2 fills the first rigid motion transformation, so option 2 is not the answer. Why? Option 2 is not the answer because the vertex or point B cannot be mapped to B prime on triangle A prime, B prime, C prime by translation. It's impossible. Okay? Alright, so we are eliminating the second one. Now let's take a look at the third one. The third one says a reflection followed by a translation. Now, if we reflect triangle ABC, what's going to happen? If we reflect it, A gets reflected to A prime, good. B gets reflected to B prime, and then C gets reflected to C prime. Excellent. So the first transformation works. Alrighty. You can get triangle A prime, B prime, C prime by reflecting triangle ABC across the x-axis. So that's good. So does that automatically make it the answer? The answer is no. There are two rigid motion transformations that have to be considered. If the first one is satisfied, it doesn't automatically mean that the second one is satisfied, okay? We have to check both of them. Alright, so let's check the second one. So the first one is good. You can get from A, B, C to A prime, B prime, C prime by reflection. Now, can you get from A prime, B prime, C prime to A double prime, B double prime, C double prime by translation? So just by shifting this to the right, can you get to this point right here? The answer is absolutely not. You cannot even get any of the points to line up with this triangle right here. Okay, so the second transformation is a total failure. So let's write down why. Option 3 is not the answer. So 3 is not the answer. Why? Why is 3 not the answer? 3 is not the answer because let's see. Because triangle A prime, B prime, C prime cannot be mapped to what? It cannot be mapped to triangle A double prime, B double prime, C double prime by translation. Is impossible. Okay? Alright, so number 3 is not the answer. By elimination, we can automatically see that the answer is option number 4. A reflection followed by a rotation. Alrighty? So let's take a look at it and see if this makes sense. So we have already established the first rigid motion transformation. We said that just by reflection alone, you can take triangle ABC to A prime, B prime, C prime. Okay, so just by going down, this transformation here is a reflection across the line across the x-axis. Okay, so that will take you from this triangle to this triangle. Now, how about the second piece, rotation? If we rotate triangle A prime, B prime, C prime about the origin, you know what's going to happen? We're going to end up with A double prime, B double prime, C double prime. Okay, so by a rotation, a counterclockwise rotation, okay, counterclockwise rotation about the origin, guess what? We are going to end up with triangle A double prime, B double prime, C double prime. Alright? So option number 4 is the answer. Alrighty, so let's write that down. So option 4 is the answer. How do we know? Because you can go from triangle ABC to triangle A prime, B prime, C prime by the first transformation is a what? Is a reflection. And then you can go from triangle A prime, B prime, C prime to triangle A double, B double, C double prime, the transformation in that case is a rotation. Alright, so these are the two sequence of rigid motion transformations that can take you from triangle ABC to A double prime, B double prime, C double prime. Alright? Okay, so let's illustrate that process to you real quick. So we have three triangles here, so this is the original one. Okay? So we claim that the first transformation is a reflection. So check this out. What I'm going to do is look at this triangle right here. I'm going to reflect this triangle, okay? I'm going to reflect it about the x-axis. I'm going to flip it downwards. Bam. You see what's happening? What we have now is, it's kind of written upside down, but you get the gist. This is A prime right here. This point is A prime. This is B prime, and this is C prime. A is upside down. Alright, so if you look at what we have over here, it matches perfectly. A prime, C prime, B prime. Okay, so we see that the first transformation from triangle ABC to triangle A prime, B prime, C prime is a what? Is a reflection. Okay, as a reflection or a flip across the x-axis. Okay, and then next, so let's flip this one also to continue from where we stopped. Now, we said the next transformation was a rotation counterclockwise about the origin. Okay, the rotation in this case was a 90-degree rotation counterclockwise. So what we're going to do is we're going to take this reflected figure and rotate it 90 degrees about the origin and see what we get. Alright, let's do it. Bam. Does that look like the final figure? Does it? Well, let's see. Exactly what we want. Okay, so here we have B double prime. Let's mark it up. B double prime. This is B double prime. This is C double prime. And then this one right here is A double prime. Okay, so you have A double prime, B double prime, C double prime in exact the same configuration as this original triangle right here. So we can see that the second rigid motion transformation from A prime, B prime, C prime to the double primes is a counterclockwise rotation about the origin. Okay, so if you want to be more specific, it's a 90-degree counterclockwise rotation. We just rotated this by 90 degrees. Okay, and then we ended up with this desired figure right here. So we can clearly see that the answer to this question is option number 4. Alright, in question number 2, we are going to be assessed on how to calculate the population density. Question 2 reads, the table below shows the population and land area in square miles of 4 counties in New York State at the turn of the century. Okay, so we have the table right here. The second column is the population and the third column is the land area. Question, which county had the greatest population density? So not only are we finding the population density of these 4 counties, we are also comparing them to see which is the greatest. Now before we get started, we are going to take a look at what the formula for computing a population density is. Alright, so your formula is as follows. Population density, let's write that down. Population density is given by the population divided by area. Okay, so that's how you do it. We're going to carry out this quotient computation 4 times in order to know what the population density of the 4 counties are. Alright, so let's make ourselves a nice little table so we can have our work nicely organized. So in the first column, we are going to place the location or the county. And then on the second column, we're going to calculate the population density by computing the quotient of the population divided by the area. Alright, we're going to use a calculator to help us out with this one. So population density is population divided by area. Okay, so let's get started with Broome County. So for Broome County, the population is 200,536. That's the population. So we're going to divide that by the area, which is 706.82. Alrighty, let's fire up our calculators and carry out the calculation. So we have 200,536 divided by 706.82. Enter. We have 283.72. Okay, so let's write that down. 283.72. Alright, next we're going to calculate the population density of the next location, which is Dutchess. Write that down. For Dutchess, we have the population 280,150 divided by 801.59. Let's calculate that. So we have 280,150 divided by 801.59, and we get the population density of 349.49. Let me just check my work again. 280,150, 801.59. Okay, so it's 349.49. 349.49. Alright, so now let's take a look at the population density for the next county, which is Niagara. So for this county, we have 219,846 for the population. Divide that by the area, which is 522.95. Put that in our calculators and see what we get. So we have 219,846 for population divided by 522.95 for the area of that county, and that gives us 420.40. 420.40. Alright, last one is Saratoga. So what is the population density here? The population is 200,635 divided by the area, 811.84. Okay, we're going to divide that with our calculators again. We have 200,635 divided by the area, 811.84. And that gives us 247.14. 247.14. Okay, so the question again was which one has the greatest population density? So we're looking for the biggest one, the biggest answer, and the biggest answer is 420, Niagara. Okay, so answer to question number 2 is option number 3. Alright, let's take a look at question 3. On question 3, we're going to be assessing how to generate solids from rotating two-dimensional shapes. Okay? Question 3 reads, if a rectangle is continuously rotated around one of its sides, what is the three-dimensional figure formed? Alrighty, so we have rectangular prism, we have sphere, cylinder, and cone. Alright, so the first one, rectangular prism, it's impossible to get a rectangular prism from rotating a rectangle because a rectangular prism does not have a circular outline. Okay, so the answer cannot be option number 1, a rectangular prism, because it does not have a circular outline. So what does a rectangular prism look like? It's just like a rectangle that's stretched. So we have something like this. Bam. It's not perfectly drawn out, but something like this. All right, so this is a rectangular prism. Rectangular prism. It's just like a box, okay? Like if you go shopping on Amazon and they ship you your product in a box, in most cases the box you get is a rectangular prism. All right, so this is not a, you can never get this as a result because it does not have a circular outline. All right, so option 1 is not the answer. Rectangular prism cannot be the resulting solid. Why? It cannot be the resulting solid because it does not have a circular outline. Okay, it does not have a circular outline. Why are we talking about circular outlines? Because we're talking about rotation. If you rotate any shape to create a solid, it's going to have a circular outline of some sort. Okay, so this has absolutely no circular outlines. It's all straight. So that tells us that it's automatically eliminated. Okay, but if we think about a cylinder, a sphere, and a cone, these three other options have circular outlines. Okay, so we want to carefully consider them because you can actually create all these three solids by rotating two-dimensional shapes. So the question is, which one is a result of rotating a rectangle continuously around one of its sides? Okay, so we're going to be making use of an applet, GeoGebra online applet, to give you a visualization of what the end result is going to look like when we rotate certain two-dimensional shapes. We are going to start with a rectangle, okay? So we have a rectangle here, and what we're going to do is we're going to rotate this rectangle about one of its sides, okay? Alright, so you can change the view of this rectangle just by moving this point all over the place, just to rotate and move it around. Okay, so now what we're going to do is we're going to go ahead and rotate this rectangle. If you rotate this rectangle about a side, do you see what shape is going to happen? Check this out. Let's rotate, 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 rotate. Bam! Ladies and gentlemen, what is that? That is a cylinder. Okay, so when you take a rectangle and rotate it about one of its sides, the resulting figure is a cylinder. This, ladies and gentlemen, is the answer to the question. Okay? How about sphere and cones? Do you know what two-dimensional shape results in their generation upon rotation? Let's take a look at it. Let's take a look at this figure, for instance. We have a right triangle, okay? Now, what do we get when we rotate a right triangle about one of its legs? Do you see what three-dimensional shape result? Well, let's do it. So when we rotate, 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 bam. Ladies and gentlemen, we have a cone, okay? So the result of rotating a right triangle about one of its legs is a cone. All right, now how about a sphere? Can you think about that for a second? Well, we've done rectangle, we've done right triangle. Let's look at circle. All right, so we have a circle here. Now, what shape do we get if we rotate this circle about its diameter. Okay, so you have a diameter there. If we rotate this circle about its diameter, check this out. Rotating about its diameter, bam, ladies and gentlemen, we have a sphere. Okay, so when we rotate a circle about its diameter, what you will get is a sphere. Alrighty, so that basically shows us how to generate the three options that we have, and the correct answer is going to be a cylinder. Alrighty. Okay, so I captured the three figures that we generated using the GeoGebra online software to generate. So let's go ahead and write down their names. This guy right here is a cone. This is a cylinder. And this is a sphere. Okay, so what did we get the cone from? We got the cone from a right triangle. Yes. And then we got the cylinder from a rectangle. And then we got the sphere from where? We got the sphere from a circle. Okay? So the question asks, which one do we get when we rotate a rectangle continuously around one of its sides? The answer to question number 3 is option 2, a cylinder. Alright? Alrighty, now let's take a look at question number 4. On question 4, we're going to be assessed on how to map shapes onto themselves with rigid transformations. We're just going to be focusing on reflections and rotations in this example. Alrighty, question number 4 reads, which transformation carries the parallelogram below onto itself? So we have parallelogram AMHT. Okay, so which transformation is going to carry this parallelogram onto itself? Alright, so in order for a parallelogram to be carried onto itself, basically when you carry out the transformation, the coordinates that we have here are going to match perfectly with the coordinates of the image of this shape after the transformation occurs. Alright, so that's how we can check numerically if a transformation maps a shape to itself. Alrighty, so let's write that down. In order for the parallelogram to be mapped to itself, all vertices, so these 4 vertices that we have here, must be mapped to themselves. Okay, either they end up where they came from, or every vertex is mapped exactly to another vertex. Okay, or onto another vertex of the original. So for example, if you have a rigid transformation that takes this point to this point and this point to that point, and those two stay the same, then it's perfectly fine. Okay, so that's just an example of a mapping that takes an object right to itself. So let's go ahead and carry out these 4 transformations on this parallelogram right here, and see which one generates a map that takes this parallelogram onto itself. Okay, so to get us started, we're going to make a table so we can keep our work organized. We're going to look at the mapping, and then we'll take a look at the we'll do the transformation first and then look at the mapping. So let's start with the transformation. We have 4 options to consider. We'll start with option number 1. For option number 1, we have a reflection, over the y equals x line, over y equals x. Okay, so for a reflection over y equals x, reflection about y equals x, what happens is that the coordinate xy gets switched to yx. So you just interchange the coordinates. All right. Okay, so what we're going to do is we're going to apply that formula to the mapping of the coordinates. All right. So what we're going to do is we're going to pick the points one by one. We'll apply the transformation. If we get that point or any other point on the parallelogram, that's a pass. If we end up with a point that's not on this any of these vertices, then that point is a fail. Okay, so let's start with point A. Point A is 4, 3. We're going to apply this transformation on this point, which is a reflection about the line y equals x. When we apply the transformation, guess what? It's going to get interchanged to 3, 4. So the question is 3, 4 one of these vertices? The answer is no. Okay, so 3, 4 is a fail because this is not a vertex. What does that mean? Transformation number 1 fails. It's not the answer. So it cannot be this one because it's mapping this vertex to some random point that's not a vertex. Okay, so it doesn't map it onto itself. Moving on to the next one, option 2. Option 2 is a reflection. Okay, a reflection over y equals negative x. Now, what's the formula for that? For the reflection over y equals negative x, for this one, what you do, if you have a point xy and you apply this transformation, it not only switches the axis, the coordinates, but it negates them also. So negative y, negative x is what you get when you reflect a point about the y equals negative x line. So let's test it out and see. Let's apply this transformation to point A again, 4, 3. If we apply the transformation, which is a reflection about the line y equals negative x, what's going to happen is that the coordinates will switch to, oopsie, not 4, 3. It's going to switch to 3, 4. It's not only going to interchange the coordinates, but it's going to negate them also. The opposite of the interchange. So this will be negative 3 and negative 4. Is this vertex, is it present on this parallelogram right here? The answer is no. We have another fail. Bam. This point is not a vertex. So this point 4, 3 is getting mapped somewhere else and is not mapped to this point or any other vertex. So what does that mean? This transformation does not carry this parallelogram onto itself. Moving along to the next one. The next one is, let's see, a rotation 90 degrees clockwise about the origin. Okay, that looks similar to what we did previously, I think on question 1 or something like that. So how do we do that transformation? For option 3 is a rotation 90 degrees clockwise. So for this one, rotation 90 degrees, not clockwise, sorry, counterclockwise. How does this affect a coordinate? So if you rotate 90 degrees clockwise about the origin, so if you rotate a point, let's say xy, 90 degrees clockwise about the origin, what's going to happen is that the coordinates gets interchanged, but only the y-axis is negated. Okay, so you negate the y-axis and interchange them. Alright, so let's apply this transformation onto point A and see what happens. So point A is 4, 3. If we apply this transformation, which is a 90-degree rotation about the origin, what's going to happen is that we're going to interchange the coordinates 3, 4 and negate the original y. So it's going to be negative 3, 4. Now, is negative 3, 4 any of those vertices right here? The answer is nope. Ladies and gentlemen, we have another fail. This is not a vertex. Not a vertex. Alright, so the last one that we're going to try out is the rotation 180 degrees counterclockwise. Ladies and gentlemen, this should be the answer by elimination, right? Hopefully. So what we're going to do is apply the transformation to the coordinates on this graph and see what happens. Option 4 is a rotation 180 degrees counterclockwise. Alright, so that one, rotation 180 degrees counterclockwise of a point xy. What that's going to do is simply going to negate the points, negative x and negative y. Alrighty? Okay, so to do that, let's apply the procedure to the points. If you apply it to 4, 3, what's going to happen? If you apply a 180 degree rotation to 4, 3, that's going to give us negative 4, negative 3. Do we have that here? Yes, point H. That's a check. Good. If you apply it to point M, which is negative 2, 3, you just negate the x, right? So this one is going to be, I'm sorry, you negate both of them. It's going to be 2, negative 3. Do we have 2, negative 3 here? Yes, we do. Point T. Check. Alright, and then the next one we have A, M, H. H is negative 4, negative 3. When we apply the transformation, we're going to negate both of them. 4, 3. Do we have 4, 3 as a vertex? Yes. A. That's a check. And then the last one is T, 2, negative 3. When we apply the transformation, we negate both. Negative 2, 3. Do we have negative 2, 3? Yes. Point M. Check. So we can see that the transformation, which is a 180 degrees rotation counterclockwise, will map this shape onto itself. Okay? An easy way to do this is by, you can, for the rotation parts, you can just rotate your paper, and then ask yourself, how does the resulting image upon rotation compare with the original one? Or you can have a nice little paper, you just cut it out, and then just rotate it and play around with it and see how the image upon rotation compares with the original. Alright, so in order to do this problem successfully numerically, you need to know what these formulas are. Okay, so this is basically how you map shapes onto themselves using rigid motion transformations. Alright, let's take a look at question 5. In question 5, we're going to be looking at how to dilate a point with the center at the origin. Okay? Question 5 reads, after a dilation centered at the origin, the image CD is C prime D prime. Okay? The image of segment CD is segment C prime D prime. If the coordinates of the endpoints of the segments are 6, negative 4, 2, negative 8 for CD, and 9, negative 6, and 3, negative 12 for C prime D prime, the scale factor of the dilation is... Alright, so to do this, all we need to know is the formula for dilation of a point about the origin. Okay, so formula for dilation centered at the origin. So the dilation of xy with the center at the origin by a factor of k. So we can write this as the dilation about the origin with a factor of k of the point xy. So if you dilate xy by a factor of k about the origin, you will end up with kx ky. So you simply multiply the x and y coordinates by the scale factor. Okay? K is a scale factor. So k is the scale factor. So that's basically what we're looking for in this problem. We're looking for the k value, or the scale factor value. All right. So in this particular problem, we're going to be going from C to C prime. Okay. So what we're doing is we're going to dilate the point. The original point is C. Now, ladies and gentlemen, we can use C or we can use D. Okay, all you need is a point to do this one. So we just picked C. If you wanted to use D, you get the same answer, so it doesn't matter. So we're going to be dilating C. C is what? 6 comma negative 4. We're going to be dilating C with the origin, centered at the origin with a factor of, by a factor of k. Okay, what is k? K is a scale factor. What is it? That's what we're looking for. We don't know what it is yet. Okay, so if we dilate 6 negative 4 about the origin by a scale factor of k, what we're simply doing is multiplying the coordinates by k. So we're going to get 6k and negative 4k. All right. Now, upon dilation, what are the values of my coordinates going to be? So C is going to get mapped to C prime. So after the dilation by a factor of k, you're going to end up with 9 comma negative 6. So what we're going to do to finish off this problem is we're going to use simple algebra to solve for our k value. Okay, since the x values are equal, we can set up the equation 6k over here. We can set up the equation 6k is equal to 9. If you want to use the x's, okay, because this is xy, is the same point, xy. If you want to use the y's, you can say, oh, the y's, or you can say negative 4k is equal to negative 6. So by solving any of these for k, you will get exactly the same scale factor. All right, so let's do both of them. So for the first one, to get k by itself, divide both sides by 6. Okay, and then that gives us, what does that give us? It gives us k is equal to 3 over 2. How did that happen? We divided the top and the bottom by the GCF, the greatest common factor. Here is 3, so divide by 3, divide by 3, and then you get 3 over 2, and that's your answer. All right, answer to question number 1 is, I'm sorry, question number 5 is 3 over 2. That's the scale factor. Okay, now, what if you wanted to use a y equation because you don't like x's? Okay, so if you wanted to do the y, same procedure. You want to isolate k, so you divide by the coefficient of k, which is negative 4. In the x equation, it was 6, so we divided by 6 so that this divides out. All right, so here in the y coordinate, the coefficient is negative 4. So divide both sides by negative 4. So that gives you a k value, k which is equal to, now, do you see what the GCF is here? The GCF here is negative 2. Or you can just reduce the sign, slash and dash, and divide by 2, top and bottom. Bam. And guess what you're going to get? You're going to get 3 over 2, the same answer. It's just a reinforcement. Okay, so we see for certainty that the scale factor for dilating segment CD to segment C prime D prime is 3 over 2. Alright, so this is basically how you dilate a point with the center of dilation at the origin. Thanks so much for taking the time to watch this presentation. Really appreciate it. We'd like to know what you think. If you found the contents of this presentation helpful to your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is extremely important to us. If you have any questions or comments, just post it in the comment section below and we'll be more than glad to respond. Do not forget to subscribe to our channel so you can get updates to the remainder of this review series and other great math tutorials to help you do well in your math courses. And for more support resources, do visit our website at mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.